Hello, we are going to be doing the Chapter 6 worksheet today. And this will be your lesson for Chapter 6 all the way through. Okay, so we're going to start with this thing called the standard normal distribution. So one property of the standard normal distribution, it's a normal curve. So it kind of looks like this. This is sort of like the x-axis. And then it kind of comes up here, peaks in the middle, and then drops back down. Another thing is property is the mean is equal to 0. And that's m, or mu there. So the middle is 0. And then the standard deviation, which is that guy, is equal to 1. Okay, and in general, not always, but this is some, well, I'll just say this is sort of like data. So I'll keep that there. So if the average of all the data is 0, peaked at 0, and the standard deviation is 1, that's called the standard normal curve. Okay, so what does the area under the curve represent? So basically this is the curve right here. This is the curve, the top part of this. That's the curve. So under this curve is area, so this shade right here. That shade right there is called probability. Okay, so what does the x values represent? These are the x values right here. Now, if the x values are z-scores and random variables, that's what they're going to be. Okay, so if these are z-scores or some sort of data, random variable, then, and it looks like this, that's a standard normal distribution, standard normal curve. Okay, so a percentile. So let me show you what a percentile is. Okay, so if that's 0, this is 1. A percentile is the area to the left side of the curve. So always the left for a percentile. So if I called this a data point and I draw a line to the top, this shade over here under that curve is a percentile. And we could find that using the normal calculator. Okay, a critical value is like this. So this is what a critical value is. So if it's 0 and 1. So these are z-scores. Usually these are z-scores. This is a z value. And this z right here is this area to the right. So essentially, it's this, we need to find the z-score, so you're working backwards. They're going to give you an area. They're going to give you an area, and then you need to find the z-score. And that z-score, with the area to the right, is called a critical value. And in a critical value, and we'll call this actually just z alpha, separating unlikely value from those that are likely. So essentially what they're saying is this. Now anything sort of around here, anything around here is just stuff that's just normally happens. That's why the peak's so high. So there has to be a point where we get farther away from the norm that we start to say, hey, something's wrong. So we'll say that that's this. That's this z-star. So we're going to call this is the z-star that separates the OK values from the extreme values. So any z-score here or higher, we would consider maybe out of the ordinary. Okay? And I'm just going to change this around. This probably should say z-score. And it's denoted with the z with an alpha, where alpha is the right side of the curve. So I'll show you where alpha is on this curve. So that's 0, this is 1, this is what we're going to be trying to find, that's z alpha. This is alpha right in here. Alpha is this little space right there. So it's usually pretty small. Okay, so let's go ahead and learn how to use the normal calculator, which is right here. Okay, so this says, now remember, these are all z-scores under here. These are all z-scores. So this is a z of 0. So when they say pz is less than 1.26, we kind of did this before when we did the 68 rule. Let me show you where 1's at. So if that's 0, actually I'll do it over here. Okay, so if this is 0, 1's always right about here. 2 is usually right about, that was kind of a bad job. 1's right about here. 2's right about here. And 3's kind of out here. So I'll just kind of leave that up as I go. So when I pick 1.26, I'm kind of landing somewhere over here. And what I do is, this says probability, this is how this reads. This is the probability that the z is going to end up being this number or less. Well, here's the number or less. What you want to do is shade, you want to shade to the left. So I'm finding that shade right there. And what I'll do is I'll stay consistent for what they do. They always do this in red. Hopefully this is red. Probably not. Maybe this is red. I'm not good with colors, so hopefully this is close to a red. It looks like it to me. Okay, so to find this shade, that's what they want you to find. Now remember, the whole curve is 100%, so this is not the whole curve, so this is going to be less than 100%. So let me show you how to do that. And then they show you how to do it right here. So this is, that's how you do it right there. Okay, so what we're going to do is we're going to go over to StatCrunch. And we're going to hit Stat. So I'm just following these things right here. Go down to Calculator. Now we want to hit Normal. I'm going to get rid of this mess. And then I'll move that thing back. I don't know where that thing went. Oh, I had to click on it. There we go. Okay, so what I want to do is keep the mean at 0 and standard deviation at 1. I'm going to change this guy right here to a 1.26. I'm going to hit enter. And 0.896. Okay, I think I could keep this out now. That I think I just wasn't hitting it right. So the answer here is 0.896. And I'll do what they said and do that decimals. So that's what I'm looking here. Okay, so now this is greater than negative 1.89. Well, negative 1.9 is like way over here. That's that number right there. So I draw a line. This is a greater than sign, greater than or equal to. So I'm going to shade that side right there. And the way you do this is you just come over here and change this to a greater than sign. And then I just put that number in there. The negative 1.89, and then just compute it. So So that's the answer for that one. So this is 0.9706. Okay, so the next one over here, this is a between. So this number right here is right about there. And this 2.27 is kind of over here. So what I'm going to do is draw a line to the top here, draw a line to the top. I'm trying to find this middle thing. Remember, the area is, the probability is always under the curve. So now what I'm going to do is, instead of hitting standard, I'm going to hit between. And then keep the mean and standard deviation the same, and I just change this to 0.12. And then over here to 2.27. And voila, 0.4406. Okay, so sometimes we're going to move on to here. Let's do this one here. So now, what this stands for is this is the percentile at 60. And if you go back and rewind a little bit and you look, 60 is what I'm looking for, the percentile where 60. I'm looking for a z-score that's bigger than 60% of all other z-scores. So I'm working backwards here. This is an actual area. So the areas are these guys under the curves. So now I know this is 60%, and I'm looking for that z-score. Okay, so just rewind and talk about, listen to what I said again if you need it. Okay, this is 60%. The middle is 50%. So I'll just show you some logic here. This is 50, and that's 50. So if it's the percentile for 60, it's going to push over a little bit and be over here. That's your 60. To find it on Stack Crunch, you have to work backwards. Let's go back to standard. Run standard. Now, what we want to do is, since we're working with the left side here, this is the left, we want to flip this to a less than sign. And now we want to come over to this right box and put in 0.6 there. So if they give you an area, that's how you do it. If they give you an area here, look, I'm over here on the left, over here, on the normal calculator. If they give you an area, you put that area in here, and then the z-score of the data will fall out here. So this answer is going to be 0.25. Really doesn't matter. I'll just do 3.3. Okay, now Q3. If you remember from before, Q3 is the third quartile, which is the third quarter. So Q3 is sitting over here somewhere. And this area under here is 75% of all the area. And you need to find Q3. To do that, all we have to do is change this guy right here to a 0.75 because it's the third quartile. There you go. See the red? This red here is 75%, and that's actually 25. That's 25%. So 0.6745. Okay, now I'm on problem 4. 4 here. Now, oh, 2 decimals, sorry. I went to 4. I looked up here. Okay, 0.04. This is a critical value. So what they're doing is they're telling you, I'm going to work down here. They're telling you this area right here is 4%, and they're saying find that this z-score. This would be a z-score that's separating the okay ones. These were okay, and these are outliers. Okay, so to do that, just come over to my normal calculator, and then since I'm working on the right side, see this is the right side right here. Yeah, that was cool. Didn't mean that. Since we're working on the right side, we want to change this to a greater than sign. since we're working on the right side. And they told us 4%, so we're going to go 0.04. 1.75. So this is 1.75. So basically what this means is that out of all the z-squirrels in the world, 4% of them are bigger than this number. Okay, now this is -2 and 2. What percent's between -2? Percent is area under the curve. So in this case we want to go between, and then just put in -2, and then on this side we want to put in 2, and it should be around 95.95. So about 95% of z's are between this value and that value. Okay, so 6.2. Now this is the same exact thing we're going to do, and I'm just going to draw a picture here. It's the same thing we just did. This is called the standard normal curve. And this is just a normal curve. Now the difference here is this middle was 0 and this standard deviation is 1. Okay, in this case, the mean could be anything. So the mean's what it is. It's like the average, and we call it mu. And the standard deviation is that guy. So basically the only difference is when it's a standard normal, this is always 0. The mean's always 0 and the standard deviation is always 1. Well, if I said what's the average height, it's not 0. So the average height would be whatever the average height is and whatever the standard deviation is. So this deals with like real data, and this usually deals with z-scores for the most part. Okay, and basically everything's kind of the same. So we're just going to jump right in there and just use the calculator. So IQ scores are normally distributed, so that's nice. So we could draw our normal distribution. You draw your normal distribution and you always put the mean here. See how that's different from the normal? And then they put the standard deviation up here. Standard deviation of 12. Then they say, what would the probability, remember probability is like area under this curve. You can see my cursor under this curve. Probability of selecting an adult male who has a higher score than 127. Well, 127 is over here somewhere. So I put a 127, draw a line to the top, and then they'll say higher. That's your keyword right there, higher. So higher is going to be over here. So then I just go to my calculator. Now I have to change the mean to what they told me, 100. Change my standard deviation to 12. And then I need to go to standard. So now I'm on standard. It says higher. Higher is a greater than or equal to sign, so I'm already there. Now I just have to put 127 here. And compute. 0.01. 0.01. So it's 2 decimals. Okay, so what that means is this little shade is around 1%. So 1% of the people have IQs greater than 127. Okay, now let's do the next one. Okay, IQs are normally distributed. Okay, perfect. A mean of 100, standard deviation of 12. Now you have to ask, are they asking for probability or are they asking for a score? Remember, scores are down here. These are your IQ scores. Probability is under here. Okay, or percent or area, however you want to look at it. Okay, so what IQ score? They're looking for an IQ score. So they're looking for a value down here for the first 25%, the first quartile. So the first 25% is over here. So they tell you this percent, and they're looking for that score right here. And that's what we do with our normal calculator. We just come over here, normal calculator, and since it's the left side, this is the left, this is the right. This is the left, that's the right. And if it's the left, we want to use the less than sign. Okay? Now, they gave me an area. This is area over here. This is probability. So where I'm erasing, that's gone. I need to put a 0.25 in there. 0.25 there, boom, compute. So the score is 91.91. So essentially, if they come back and they're like, hey, you got a 91.91, you basically beat, you're better than, or you beat 25% of everyone. Okay, I guess that's good in a certain way because you beat 25%. The bad way is 75% of the people beat you. Okay, let's go next. Okay, let me get out of this real quick. Whenever they say normally distributed, I automatically draw a curve. So women's height are normally distributed, okay? So I'm going to draw the girls here. They have a 69.5 and a 2.4. Oops, that's the guys. Okay, the woman 63.8 and standard deviation of 2.6. Which doesn't make sense, but whatever. Here are the girls. Okay, find the percentage of women that meet the height requirement. Okay, so let's see. Find the percent of women. So I'm working on this curve that meet the height requirement. Okay, so what's the height requirement? 4'8". So 4'8", that's 4 feet. You have to do a little conversion here because they give us inches here. These are all inches. So 4 feet, that's 12 times 4. That's 48 inches. So 48 of the inches are coming here, and I have 8 more inches. So I need to add 8 to that. So that would be 56 inches. So I'm gonna check. The shortest you could be is 56. What's the tallest you could be? 6'3". So 6. There's 12 inches in a foot, so there's 12 of these. So that's 12 times 6. That's 72. And then there's 3 more inches, plus 3. So the tallest you could be is 75. So 75 is like over here somewhere. So all these people in here meet the requirement. All these girls here meet the requirement. So that's that shade right there. So this is a between. So I go here, between. Change my mean. Change my standard deviation. And this is going to be my lower. This is going to be my upper. It's going to be pretty much everybody, but 0.998. I don't know how you round that to 2 decimals, but I'm going to go to 4. Okay, so that's how you do that one. Now, let's do this one right here. Okay, so it's the same question, but it's for males. So now I'm just going to do the same thing over here, 56 to 75. Now with this one, all I have to do is just 56. All I have to do is change the mean and standard deviation. Because they're asking for the guys. I got something wrong here. this is better. 56 to 75, 69.5, that's over here. 2.4, that's over here. And I'll just do 0.99 for this one. So that's 0.99 for that. Okay, so let's do this last one. This last one's going to be a working backwards. And just trying to move this up. Wish I kept that little thing there. Okay, so let's do this one. Okay, so if the hierarchy, we're going to exclude the tallest 3% of men. So the tallest 3% of men. So the men are 69.5, and the standard deviation is 2.4, and then we want to exclude anybody that's this height or more. Anybody that's this X or taller is going to be excluded. So this percent right here is 3%. So what you want to do to find the tallest person now, because they're asking for what's the new height requirements. So since I have guys in here, I'm going to come over here. I need to find the height that excludes the tallest. See, this is a less than sign. I need to change that to a greater. And I need to put a 0.03 over here. Because they gave me a percent, so 74 is the tallest now. So the new tallest, the tallest you could be is 70, pretty much 74. Now what's the shortest? Shortest 3%. So to get the shortest 3%, I have to go to the girl distribution and say, okay, well, if a girl is shorter than this value, if a girl is shorter there or more, this is 3%, they can't do it. So this is 63.8, and this is 2.6, and this is a less than. I need to change the mean to 63.8, and the standard deviation needs to be 2.4. And then I need to change this to a less than, and this needs to be 0.03. You can see this picture is going to look like my picture. There's just prettier. So the shortest is now going to be 59.3 inches. That's the shortest, that's the tallest. Okay, so that's it for the second section. Just basically you have to get good at working in your normal curves. Okay, so a sampling distribution. This could be a little tricky. You will not have any homework on this. There's no homework. But you do have to have the idea down pretty decent. You have to have the idea down. So I don't want to take this too much for granted. It's actually really important, but okay, so basically what this is saying is the sampling distribution of sample mean is the distribution of all possible sample means from a sample size n taking the same population. So it's a little tricky, but basically if this is your population, so that's like your population. If you take a sample from there and you get an average, that's an average. And you take another sample, get another average, and get another average, and get another average, and get another average. You just keep sample, and all these samples have the same size. These x-bars are not going to be the same. So basically what sampling distribution is, it's the same graph, but the data are not like heights or IQ scores, the data are like x-bars, okay? So that's what a sampling distribution is. And there are two of them. There's also one for p-hats and there's one for x-bars. So the sample mean target the value of the true mean. Mu's the true mean. The distribution of the sample means tends to be a normal distribution, which is good because then we could use this guy. Okay, the sample and distribution of a proportion, the data would be different. So here, this is more like for voting. So this is like the true vote rate. But if you take a sample and you get the percentage of people from the sample, that's called a p-hat. If you take another sample, that's another p-hat. So the only difference between this distribution and this distribution is the data that's collected. Here the data is quantitative, and here the data is categorical. Okay, sample proportions, calculate, they're true. So all these p's, there's a whole bunch of p's. Every sample p hat is probably going to be a little different. All these p's target, all these p hats, this is called p hat. All these p hats target the truth. The distribution of the sample proportions tends to be a normal distribution, which is nice because we could use this to solve the problems. This one here, you're going to have to do more. This one here is the one we're going to be working with. Okay, you have to know these. You have to know these notations. The sample mean is an x with the line over it. We call that x bar. Population mean is mu. The sample proportion is a p with a little caret, which we call hat. And the population proportion, which is the truth, which is p. Okay, now, when you take a sample, we want this guy to unbiasedly be close to this guy. Okay? So we want these guys to be unbiased estimators of these guys. And good unbiased estimators are these. Unbiased is a good thing. So if you want to know the true mean, take a random sample and get x bar, and that should be close to this guy. That's what it means to be unbiased. Now bias estimators are these guys. And all I'm saying, all this is basically saying is if you have a population and you're interested in the median of the population, and you take a sample and you get the median, you find the median from the sample, generally that's not good at predicting the true median. That's basically what we're saying. Okay? So we're actually going to not do the problem here because you're not going to have homework on this, but there is going to be a part that we have to kind of talk about. That's called the central limit theorem. Okay, so maybe go back and watch that section again, just to get a little idea, or just do some research on sampling distributions, from your book. Okay, so the central limit theorem is really important. This is something that's highly missed in the class, so you really want to pay attention. For a population with for a population with a, let's see, I'm going to kind of take this over here, with a skewed distribution. The distributions of the sample means approaches a normal distribution if the sample size is at least 30. So that's at least. Okay, so basically what that's saying is if you have this population and you graph the population data, it looks horrible, something like this. And then remember, the sampling distribution is a graph of x bars. So all these x bars are being pulled from this population. So sample, 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 sample. Every sample you get an average. If you graph these averages, they turn out to be normal. Okay? Now, what if you don't have 30? So there's some tricks around it. If the original population is normal, then you don't need 30. You could have any size. The sample means will be normally distributed. If the original population is not normally distributed, then you need 30. And then this is always true. So this is a must. You have to know this because see where it says mu right here? Look over here. This is your mu. This is a standard deviation. If you look over here, that's your standard deviation. So this formula, you're going to have to put this formula in over here. This mean is going to go over here. Okay. Clear this stuff out. Okay, so I'm going to keep that there. Now, let's see if the central limit applies. I need to keep that other part out. Okay, we're going to be looking at these to answer these questions. If the central limit theorem applies, if n is 20, so as soon as I see this 20, I'm like, hey, I don't have 30. So that's not met. The original population is not normal. So this is a no. Okay? This is a false. Think about it for a second. This is what you should be looking at first. Is the population normal? Is the population, not that, sorry. We're looking at the population, so population is normal versus population is not normal. So let's start with that. Is the population normal? It's not normal. So if it's not normal, then you need at least 30. Well, how many did we pick? 20. Well, 20's not at least 30. 20 is less than 30. So 20 is not at least 30. So this is a false. Okay, the original population is normal. The original population is normal. Okay, how many can we pick to get normality? Any size. So this is any size, so that's a true. Okay, so if the central limit applies, let's look at this population. The original population is not normal. Okay, up here, not normal. How many do we need? 30 or more. Should come back down. Hey, do we have 30 or more? Yes, we have 40. So that's a true. Okay, let's look here. The original population is normal. This looks like the same. Oh, that's not normal. Okay, original population is normal. Come back up here. Population is normal. How many do we have to pick? Any. Come back down. 40 is any. So that's a true. Okay. So go through that a few times and just kind of get the hang of it. Now we're going to do, do this stuff right here. Okay. In a population of 210 women, nope, yes. So a population, so that's your population. The heights of women are normally distributed. So they just told us that the population is normal. Okay, if 36 are women are picked, they give us the mean and they give us the standard deviation. Now they picked 36, see? If 36 women. Now let's see if we could use the central limit theorem. Let's see, the central limit theorem allows us to use these guys. So, it's normally distributed. Normally distributed, I come up here. Original population is normally distributed. How many am I allowed to pick? Then for any size. 36 is any size, so we're good. Now it says find the mean and the standard deviation. So the mean of the x bar is whatever the mean is, see? So what was the mean they gave us? 64.4. Okay, so it's either going to be A, C, or B. Standard deviation. The standard deviation is going to be this guy, which is the original standard deviation, which was 2.9, divided by the square root of 36. This is n. That's how many we selected. That's what your n is. Your n is 36, and this is 2.9. Okay, so now we just have to put this in your calculator, which is 2.9 over 6, and let's see, it's definitely not A. It's definitely not B, so it's C. Just pull your calculator out and put that in your calculator. Okay. The overhead reach of an adult normally distributed. So they're telling you that it's normally distributed. So we could have any size. This is mu. That guy's sigma. Find the probability that individual distance is greater than 210. So let me just get a little more space here. Notice on this problem, how many are we picking? An individual. An individual is one person. That's not a sample. A sample has to be 2 or more. So this is the same thing we did in section 6.2. So I'm at 197.5. It's normal, so I'm going to be able to use this curve. What's the standard deviation? 8.3. Greater than 210. 210's over here. Greater than's over here, so I'm trying to find that shade. Okay, so I'm going to come over here, change the mean. Okay, standard deviation 8.3. Now I'm going to change this to a greater than sign because I'm dealing with the right side. They gave me a data, so I'm trying to find a percent, so that's going inside here. So 0.210.9, okay, good. So this is 0.053 and 2. 0.0532. Okay, so that's that. Now what's the difference between this problem and this problem? Because it sort of sounds the same. Find the probability. Find the probability. Okay, this says individual, but this says mean for 20 randomly selected distances. So my n is 20. Okay, my n is not, my n was 1 here. My n is 20, that's the difference. Okay, now they're asking for a different number. Okay, so my mean is 197.5. 196 is over here. Draw a line up. It says greater than, so I need a shade over here. But now we need to use the central limit theorem. Let's see if we could use this. We can use the central limit theorem because they told us that they were normally distributed. See, I'm up here. It's normal. So what size? The size can be any size. We have 20. So we're good. Now what's the central limit theorem says? The central limit theorem says the average of all the x bars, because these are x bars down here. These are all x bars, is the same as mu. So what that means is we come over here and we should have a mu of 197. Perfect, 197. This is the trick. The standard deviations of the x bars is not sigma. Standard deviation of x bars, standard deviation spread. You're going to have less spread in x bars because you're taking samples, and samples are closer to the truth. Okay, so if every sample is closer to the truth, then you're going to have less spread around the truth. This is the truth. Okay, so it's going to be sigma, which is the original standard deviation, divided by how many people you picked. So what you have to do, get rid of that thing. What we have to do is come over here, put the original in, which is that. I'll start from scratch though. The original is 8.3. Now you do a divided by sign, and you type in SQRT. That stands for square root. You put in how many we picked, which was 20. Okay, we're still at greater. They said greater than 196. And hit compute. So 0.79. So that's the key. When you take a sample, you have to remember to take the square root of how many people, you have to take the original standard deviation divided by the square root of how many you picked. Okay, this is going to be our last one. We're going to do this. This is going to be it. I'll just answer it. Why can we do the normal distribution part even though it did not exceed? Because the original distribution was normal. That's why you could do it. Okay, so the weight of fish in a lake are normally distributed. So I'm doing the population right now. Mean of 20. Standard deviation of 9. Now, this is the original distribution. What that means is they're individual fish. So everybody in this, all these fish, all this data is made up of each fish. Now we're going to take 9 and get an X bar. So this distribution is made up of all possible X bars of size 9 from that lake. Okay? Now, can we use the central limit theorem? Let's take a look. Because we only have 9. 9 is not 30. What's the original distribution? The original distribution is normal. Since the original distribution is normal, we could use any size. Okay? So we could use that. So the way it looks is the average of all these X bars is mu. Okay? Here's mu, which is 20 pounds. So 20 goes there. Okay? What's the standard deviation? The standard deviation, that's why I put these X bar here. This standard deviation is called standard deviation X. This is standard deviation of X bar. What's the standard deviation of X bar? Which is the original standard deviation, which is 9 over the square root of how many we picked, which is 9. So it's 9 over the square root of 9. Well, this one's a little easier because standard deviation is 3. Standard deviation is not 9 anymore, it's 3. So I come over here. We could use the normal calculator because the total is normal. We could use the CLT. Okay, mean is 20. Standard deviation is 3. I didn't have to do all that funny business because it came out perfect. And I think this is a between problem. Between 17.6 and 17.6 and 23.6. So 0.67. So the answer here that's your answer. Okay, so I did a couple examples like that. You guys could go back and watch them. And that's it. So hopefully it was helpful.